Good morning, everyone, and welcome to today's presentation. I'm Dr. S.K. Singh, and I hold a PhD in this field. Today, we'll be exploring the important topic of linearity criteria in analytical method validation. Over the course of this session, we'll discuss what linearly means in analytical methods, why it's crucial for validation, and how we can effectively evaluate it. I'm excited to guide you through this essential aspect of quality assurance in analytical chemistry. Let's get started. Welcome to this section on method validation. Today, I'll walk you through the key parameters as outlined by USB, which are essential for ensuring our analytical methods are reliable. First, we have accuracy, which tells us how close our measurements are to the true value. Then, precision refers to the consistency of our results, whether repeated under the same conditions or across different days. Specificity is about the method's ability to distinguish the analyte from other components. Linearity shows how well our method can produce results that are directly proportional to the concentration within a given range. Range itself indicates the span over which the method remains accurate and precise. LOD, the limit of detection, is the smallest amount we can detect, while LOQ, the limit of quantification, is the smallest amount we can measure reliably. Robustness tests how resilient our method is to small changes in conditions. Moving on, analytical method validation is crucial because it ensures several key qualities. Accuracy and precision, as I mentioned, are fundamental. Specificity is vital to confirm the method's ability to measure what we intend. Sensitivity, which includes LOD and LOQ, helps us detect and quantify even very low levels. And finally, reliability. This is what gives us confidence that our method will perform consistently in real-world applications. All of these parameters work together to ensure that our analytical methods are trustworthy and compliant with regulatory standards. Let's start by understanding what linearity means in the context of USB. Essentially, linearity refers to the ability of an analytical procedure to produce test results that are directly proportional to the concentration or amount of analyte present in a sample, within a specific range. In simpler terms, if you increase the concentration of the analyte, the response from the detector should increase proportionally. We often express this as response is proportional to concentration. This proportionality is crucial because it allows us to accurately quantify the analyte in different samples. Now, moving on to the purpose of conducting a linearity study. The main goal here is to ensure that our analytical method provides accurate and reliable results across the entire working range. We want to confirm that the detector response is proportional to the analyte concentration, which underpins the accuracy of our measurements. This proportional response also contributes to the reliability of the calibration curve we establish, making sure it truly reflects the relationship between concentration and response. Finally, establishing linearity is vital for the suitability of our methods, especially when we're measuring both active ingredients and impurities. A good linearity ensures that our quantitative results are consistent, dependable, and compliant with standards, which is essential for quality control and regulatory approval. This is why understanding and verifying linearity is such a fundamental step in method validation. Let's talk about the range for linearity in USB practice. When we're working with assay methods, the acceptable range is typically from 80% to 120% of the test concentration. This means that within this span, the method should produce results that are directly proportional to the concentration of the analyte. For impurity methods, the range extends from the limit of quantification, or LOQ, up to 150% of the specification limit. This ensures that we're accurately measuring impurities across relevant levels, from the lowest detectable amount up to the maximum allowed. Now, regarding the number of concentration levels, the minimum we usually need is 5. But to get a more reliable and robust assessment, 5 to 7 levels are generally recommended. Overall, these ranges and levels are designed to ensure our methods are precise, accurate, and reliable within the specified limits, which is fundamental to maintaining quality and compliance throughout the testing process. Let's take a look at the concept of linearity data, using this example to illustrate the process. When we talk about preparing linearity solutions, we're essentially creating a series of standards with known concentrations to test the accuracy of our assay method. In this example, we're aiming for a target concentration of 100 micrograms per milliliter. The key idea here is that by preparing these solutions carefully, we can plot their responses and verify whether our method produces a linear relationship across the range. This helps us ensure that our assay can reliably measure samples within this concentration range. So, when preparing these solutions, precision is crucial, as small errors can impact the entire calibration curve. This step is fundamental to validating the method's linearity, which is a cornerstone for ensuring the accuracy and consistency of our analytical results. Overall, this process connects to the broader theme of method validation, making sure our analytical techniques produce trustworthy, reproducible data. Let's take a closer look at plotting the calibration curve. This step is crucial because it visually represents how well our model's predicted probabilities align with the actual outcomes. By plotting the predicted probabilities against the observed frequencies, we can see where our model tends to overestimate or underestimate risk. The key here is to focus on the calibration plot's diagonal, which indicates perfect calibration, meaning our predictions match reality perfectly. Deviations from this diagonal highlight areas where the model's predictions are less reliable. This visualization not only helps us assess the current model's performance, but also guides us on how to improve it further. In the context of our overall goal, understanding and improving calibration ultimately leads to more trustworthy and actionable predictions. Let's go over the acceptance criteria for linearity. First, the correlation coefficient, or R, is a key indicator of how well our data fits a straight line. For assay methods, we typically want R to be at least 0.999, which shows an extremely strong linear relationship. When it comes to impurities, the threshold is slightly lower, with R needing to be at least 0.995. Another important point is the y-intercept, which should be close to 0. This means that when our concentration is 0, our response should also be near 0, indicating there's no bias. We quantify this by looking at the percentage y-intercept, which should be less than or equal to 2%. Additionally, residuals, the differences between observed and predicted values, should be randomly distributed. This randomness confirms that our model is appropriate and that there's no systematic error. All of these criteria are aligned with our internal SOPs and USP expectations, ensuring our method is both accurate and reliable. In summary, the correlation coefficient tells us how linear our data is, with very high values indicating a perfect fit. Keeping the y-intercept close to 0 and residuals randomly scattered supports the overall validity of our linearity assessment. Now, let's take a closer look at the percent y-intercept calculation. This is a crucial step because the y-intercept tells us where our line crosses the y-axis. In practical terms, it represents the value of y when x is 0, acting as a starting point for our regression line. Calculating this accurately helps us understand the baseline level of our dependent variable. Remember, understanding the y-intercept is key to interpreting the overall regression model and how well it fits our data. So, as we go through this calculation, keep in mind how it connects to the bigger picture of predicting and explaining our data trends. Let's take a closer look at the linearity for the impurity method. For this example, suppose our specification limit is set at 0.2%. When we assess linearity, we consider a range starting from the LOQ, or limit of quantification, which is 0.02%, up to 0.3%, which is actually 150% of our specification limit. Now, what do we look for to confirm good linearity? First, the acceptance criteria include a correlation coefficient, or R, of at least 0.995. This indicates a very strong linear relationship between the concentration and the response. Additionally, we want to see that the slope remains consistent across this range, meaning the response increases proportionally with concentration. And finally, Low residual error is essential. That's the difference between what our model predicts and the actual observed data. It should be minimal to ensure accuracy. Connecting this to the overall theme, establishing linearity within this range confirms that our method reliably measures impurities across relevant concentrations, ensuring confidence in our analytical results. Let's take a moment to understand the difference between linearity and range. Linearity refers to how a change in the input results in a proportional change in the output. In other words, if you double the input, the output should also double, maintaining a straight-line relationship. This is important because it ensures predictability and simplifies analysis. On the other hand, the range is about the scope of values that our system or measurement can handle effectively. It tells us the limits within which our data or system operates reliably. Recognizing this distinction helps us better interpret data and design systems that are both accurate and functional within their intended scope. So, while linearity is about the relationship's nature, the range is about the boundaries within which that relationship holds true. Let's wrap up with the key takeaway on linearity. Essentially, linearity shows us that the response from our assay is proportional to the concentration we're testing. This is crucial because it means our method gives consistent and predictable results across a range of concentrations. We evaluate this proportional response using regression analysis, which helps us determine how well our data fits a straight line. A vital part of this is the correlation coefficient. It must meet specific acceptance criteria to confirm the method's linearity. This aspect is especially important for both assay methods and impurity testing, where accurate quantification is critical. If the method isn't linear, our results could be misleading, which is why this step is mandatory under USP 1225 validation guidelines. In summary, establishing linearity ensures that our analytical methods are reliable and accurate, forming a core part of method validation and overall quality control. For further support, please don't hesitate to reach out to us. We're here to help with any questions or additional guidance you might need. Just contact us through the provided channels. And with that, I want to sincerely thank you all for your time and attention today. Your engagement is what makes this worthwhile, and I hope this presentation has been helpful. Remember, we're here to support you every step of the way. Thanks again, and have a great day.